Hello guys, in this video I will be talking about vertex animation in Unreal Engine. And by vertex animation I mean animating static meshes using the material like those houses. Actually this is first part of the tutorial about the plugin we are making called it is Vertex Anim that allows actually doing this kind of stuff directly in engine. And in the next part I will really give the overview and explanation how to use the plugin, but in this first part I will just talk about the basics of vertex animation in Unreal, how it works, and things you have to make attention to. And then then I will also talk about this particular technique, call it Pivot Painter 2, which is used here in all those examples. And I will use the plugin a little bit to show you how it works on the inside. But we will start really by something very basic. We'll take a mesh and try to animate it. So we will just go here, take the default cube like so, and there I prepared a material that we will now expand. For now just the color, so I will make already a instance on this material and put it here. So we have our cube, green cube, nothing happens. Cool. Now let's try to move it. Okay, so we will go here in our material. So all the vertex animation we'll be talking about in Unreal is made possible because there is this material output, call it world position offset. And this is an offset you can specify for each vertex of your mesh. So here it's important to remember from the beginning that it's world space offset. Okay, it works in the world space, in the level space, and not in the space of this mesh. And it's an offset, so it will be added to the position of the vertex in the world. And yeah, obviously it's a vertex position offset. So this code, the whatever goes here, will be executed for each vertex and not for each pixel. So it's the vertex shader. Okay, so let's try to move the thing. We will create here vector that will be all our offset. We will make that a parameter directly, and we will call it slate, and then we will put it into world position offset. Okay, so it's 0, nothing happens. That's okay. We will apply, and here we will take our stance, make it small, and we will start to moving stuff with that. So that's our translate. And let's see what happens if I put something in the blue channel. So the blue channel is the Z, it's the blue arrow here. Oh, sorry, I should say Z axis, no? So that's the Z axis, and if I put some number here, you can see our cube is going up on the Z axis. And then if I put some value in the green, which is the Y axis, which is going, in this case, going towards me. Oh, that's still the blue. it will go towards me and in the other direction. And obviously red here you got right and left. Okay, so that's good. So there's two things to note. First of all, as I said, this thing is in the world space. So if I want to, like, if I rotate this cube, it will still go up. Okay, you see, that's means it's always go in the world space, in the space of this level. And the second thing you can see, there's those strange stuff appearing with the shadows that we will need to fix. So let's start with the shadows thing. It happens because actually when we move the cube, we are actually not moving the actual cube. We're just doing something in the material. And if you look at the bounds of the cube by doing show flag dot bounds 1, you can see that the bounds of the cube still are here. So that interferes with the rendering system, because the rendering system uses the bounds of the object in order to calculate the shadows and not deleting them properly. And to help with that, we can do two things. Basically here, if you select the cube, if you tap bounds, we have this bound scale. So we can just up the scale, and then this cube actually can go anywhere inside those bounds. So now I don't have problem anymore with those shadows if I stay inside the bounds. If I got outside, I still have the problem, of course. And then the other way to fix it, it's to edit the cube itself. And also you look for bounds here. And you can specify positive and negative offset. So for example, here I can put like 500, and you see the bounds now go up like this, and you can also see that in the level. But as you can see in the level, this is in the cube local space. We rotated it, so it goes here. Which brings us, I just undo this, I close it, which brings us to the point number 2. What happens if I want to move this thing in its own local space, which means it will always move in each one in its own axis. If it's like Z, it will always move according to this axis here. So it will move here. And that is also pretty simple. I will go here. We will take this translate vector, and we will transform it. Transform. Oh yeah, I'm already here. Transform vector. From here we have different options. So what we are looking for is the from local space to world space. Or probably you will prefer to use instance and particle space, because if your mesh is an instance static mesh, which kind of makes sense if you use a vertex animation for something like grass, for example, you will have static meshes. So in this case, this is the correct source. And For the normal static mesh, it's the same as the local space. And then you put it here and apply. And now if I rotate my cube here in the level, and if I move it up, it will go in the local space, as you can see. So until now we were moving our cube using the material parameter like this. But now if we want to move our cube automatically, like you see on all those examples, they're animated automatically. We will now go and modify our material to do this. So here there is our translation parameter, and we will take the time value, which is more or less the game time, and we will for example take the fractional part of the time, so it will be between 0 and 1, and then simply multiply the maximum translation by this. Apply, and now if we increase our maximum translation, we see that the cube will start to moving. If we want to move it like back and forward, we can also, instead of this, take the sine time, which will be between 0 and 1, and then multiply it by the translation vector. Apply, and our cube is animated like this. And if we want to like move it slowly or fast, we'll multiply the time by something, which we will call speed. It would be 1 by default. And then here we can change the speed to, for example, UE5. This will go more slowly, or to 2. So you see, it's pretty easy to animate like this. To make the effect more interesting, we can also animate other material parameters. Like, for example, here we see those houses are assembled from the pieces that appear from nowhere, or for example this car too. And we can achieve this effect by animating the opacity. Let's do this. We can take our value here, which is between -1 and 1, and animate the opacity mask. Let's make our material mask it, and here we will also enable jitter opacity mask so it appear more smooth. Then yeah, for opacity mask we need the value between 0 and 1, so we will simply remap this sine output to that. So we will multiply it by we will add 1, so it will be between 0 and 2, and divide it by 2. It will be between 0 and 1. Put that into opacity mask, and as you can see, our cube will appear and disappear now. So that's how those effects are done here or here. One interesting thing that we can observe is this setup is if you check the number of instruction, you see that the pixel shader has 199 instruction and the vertex shader 172 instructions. So when we disconnect now the opacity mask, you see that pixel shader number of instruction is lower and the vertex shader instructions are the same. So this means that unlike the world position offset, which is evaluated in the vertex shader, this calculation for the opacity mask will be evaluated per pixel. So for every pixel of our cube on screen, instead of just 4 and just 8 vertices, and which means that is a lot more times this calculation will be made. And if we want to solve this problem, we can add here a vertex interpolator node, which will actually move this code into vertex shader and interpolated it between pixels. So if we check now the number of instructions, if we connect it to opacity mask again, we see that now we have 196 and 177. So all this stuff here was moved to the vertex shader, and in the pixel shader there is some other instructions because you still need to interpolate it. Now that we've seen how the translation works, let's check the scale and then the rotation. So for the scale, what we want to do is to move the vertices of the cube towards the center of the cube or away from the center. So we will take the center of the cube, which is object pivot point, which is actually nothing else that 0 transformed from local space to world space. So we will directly use this for clarity. And we will subtract the position of the vertex from this, and then multiply that by our scale. Let's say 0.5, and then put that in the fourth position offset. And as you can see, our cube is now scaled. If we change it here, we actually need to change it a little bit more because it goes in, it's inverted. So we have to here to put 1 minus. And now our scale is working. 1, 2, 0.5, etc. Another way to do this that I learned recently is to, instead of world space, we can use actually camera relative world space. So the reason for this is that the world space, in case of large world coordinates, will use a double, and so the calculations here will be made using doubles, and this is slower that you calculate using floats. In this case, there's not a lot of calculation, but you can imagine you have something more complicated, and then it will take more time. So EPIC documentation suggests to now with large world coordinates use it camera relative world space. We change it here, and we also change it here to camera relative world position. And if everything goes correctly, we have exactly the same result. So which what is exactly is the camera relative world position? So it's like this: a camera space. It's like exactly where the camera is at 0, and the forward vector is like where we are looking relatively to the camera. And camera relative world position is it's the origin is where the camera is, but it's not rotated, it's just translated. So the forward vector is still the world vector. And it helps to reduce the number of double calculation in the shader. So that's it for the scale. Now let's make our cube rotate around the center. We'll go into our material, and for the rotation it's a little bit more complicated, but Unreal provides us with the node that does the job. So let's search rotate around about axis, and this is the node we need. So this node requires axis, angle, pivot point, and position. So that's the position we are rotating. But we will create a parameter for the axis, and that it should be normalized. So let's directly put a correct thing here. And then again, it is axis in the world space. So if we want to convert it to local space, we have our transform. Local space to world space. Dark. Then angle. This is how many we want to rotate, and this angle is between 0 and 1. 1 corresponds to the full rotation. So let's, for example, put our time here, and it's periodic, so you don't need to put the fraction here. Now pivot point will be our center of the cube. So if you remember to make a center we take zero vector and transform it into from local space to camera relative world space. That's the center of the cube. And now the position will be also camera relative. Camera relative world position. Okay. And now if everything goes correctly, our cube will be rotating, and it is rotating. But you can already notice some strange artifacts. The strange kind of shadow. And this is because this is the problem with the normals. We rotate the cube, but the normals world space normals are incorrect. So if we show them here, oops, you see that our normals are rotating too. So for example, those are world normals. So for example, if you look on this wall, all this wall is green, and this wall is all red because the normal in the world are the same for this direction. So we need to basically fix this problem with the normals. And then there's also a node that is already existing, and it's called fix rotate about axis normals. So rotate about axis, it's the node here, and that's the node for the normals. So we'll put the angle, the same angle here, and the same axis here. And here we will have a tangent space vertex normal. So the normal is evaluated in the pixel shader, and if we want to optimize this, we will insert a vertex interpolator right here, so that all this calculation went to the vertex shader, and it's only calculated for the vertices of the cube and then interpolated for the pixels on screen. And now you see that the normals are in the world space are correct, not rotating anymore. And if we return to the normal view mode, we see that our cube looks fine. Now let's push things a little bit further and add a normal map to our cube. So first of all, where we will plug it in this setup. There's here world space vertex normals input. So one thing we can do is to transform this into world space. It's already correctly set up by default, tangent space to world space. And if we apply this, we will see that nothing changed because our calculation, because of this, our calculation is in the vertex shader. So this texture is sampled only on the corners of the cube, and that's not what we want. So if we just remove this, apply, then it works totally correctly, as you can see. But now we move it everything into the pixel shader, and that's not what we want probably. So the solution exists. It's written here and said it's recommended that this be calculated in the custom with input. The resulting output data should be used as base normal in the blend angle correct normals material function. So custom UVs, it's the same thing that Vertex interpolator. So we will insert this blend axis corrected normals here. That should be our base normal, and this texture should be our additional normal. And then we put that here, apply, and it works, and works in the pixel shader. I'm sorry, it works mostly in the vertex shader. But if you look closely, you see that there is something weird. It's this shadow on the top. This shadow should be, in theory, always on the side opposite to the light, but it's rotated. It's rotating now. And that it's actually the limitation of this node. It works good if you don't rotate too much. But here we are rotating 30, 60 degrees. And also it works good for the sides, but for this side, which is perpendicular to the rotation axis, also it doesn't really work. So the solution to this exists. We made in our plugin another node that corrects this those normals in the way it should look. I will not go here into details. I will explain that in the next parts of the tutorial. But basically, we can see here, if we take this node and we put here the correct axis and the correct angle, and then here we put our texture, and then we put that back to the normal output. No, we are not using this anymore. Then, as you can see, now everything is really working correctly from all sides, in all angles. The last thing I would like to talk about is the problem of the smearing that often occurs with Vertex animations. Here we have two cubes. The cube on the left is our original cube, and it doesn't have any smearing problem. And the cube on the right uses slightly modified material, as you can see when I pause the Unreal. The text on this cube, especially on the top, it's completely blurry and not sharp at all. And that's the artifact we're looking at. And so let's see what is causing this problem. So this cube, as we've seen before, this material is just the time material node that drives the rotation. And this other material that has the smearing problem, the time material node was replaced by a material parameter, which is also called time. And as we just seen before, we had the problem, the artifact that appeared. This parameter is driven by a blueprint, which simply use set scalar parameter value on tick and put there some value, get time and seconds multiplied by 2. It could be something else. It could be user input. It could be whatever you want. So to understand why the smearing occurs, we should look at the default Unreal anti-aliasing method called temporal super resolution, or TSR. And this anti-aliasing method requires the motion vectors. So the motion vectors, you can visualize them if you go down, show visualize motion blur. And it's basically for each pixel on the screen, its velocity. So the difference in the position from previous frame divided by the delay between two frames. And as we can see, the cube on the left, which works correctly, it has all those motion vectors in place. And the cube on the right for the Unreal anti-aliasing system, it's like it's not moving, and that's what causes the artifact. So to solve this problem, there's a node, call it previous frame switch, that we can put here and put our time here like current frame. So it has two input, current frame and previous frame. Current frame is basically what we had before, and the previous frame is the frame that we passed in the previous frame, in the previous time. So it's the previous value of the time, if you want. And this works because the world position offset input, it's just one input, but actually it will be executed twice with this value first time and this value for second time. And the difference, it will be a difference between those two results will be will create the motion vector. So that is the distance between two offsets. So that in the case of the time material node, you don't need to use it because Unreal will automatically, in the first of those two offsets, use current time, and in the previous offset, it will automatically replace that by the previous time. But if you use a parameter, Unreal doesn't really know how to do it. So you need to help Unreal and give it another value here. So we, for example, will do it like this. We will create a previous time parameter, and in our material, in our blueprint, we will make a variable previous time, and then simply pass this variable here. So set scalar parameter value of the time, and then of course we need to record it for the next tick. So the next tick we will take our current time here and pass it as previous time. And if compile this, and if I compile this, now if I play, you see that both cubes have now correct motion vectors. And if I show it like so, and I pause it here, you see that both text on the both cubes are sharp. So that's how you solve this problem of smearing. That will be all for this part. We've seen how to animate a static mesh using the material, translate, rotate, scale, etc. And in the next part, we will see how to make animations such as those, where we animate separate parts of the mesh independently. So we will be looking into pivot painter technique, and also how to use the plugin Vertex Anim to make those animations directly in Unreal Editor. Oh, See you in the next video.